Yes, it is started. Hi, everyone. Welcome to our second part of the invited talk. We'll have two in the invited talk. I will first introduce Christina, our first speaker. Christina is an assistant professor and is John from the Cornell University. She has been working on computer architecture and computer systems. She specifically focused on improving the performance predictability and resource efficiency for large-scale cloud infrastructures by revisiting the way these systems are designed and managed. Christina has received a lot of the awards, such as 2020 TCCA Young Computer Architect Award, Intel Rising Star Award, Microsoft Research Faculty Fellowship, NSF Career Award, and 2 Google Research Award, a Facebook Faculty Research Award. Christina's work also received 4 IEEE Micro Top Picks Awards and several Best Paper Awards. Before joining Cornell, Christina received her PhD from Stanford University. She had previously earned a master's degree from Stanford and a diploma in EE from National Technology University of Athens. Christina, thank you again, and thank you again for giving the talk today. And Christina will talk about leveraging ML to handle the increasing complexity of the cloud. Christina, please.
Great, thank you. Thank you very much for the introduction, and thank you all for joining in. So what I'll do today is tell you a little bit about the work that we do on using machine learning to improve the design and management of large-scale cloud systems. And this work is done by my students who are all listed on the slide. So first of all, let me tell you why you might want to use ML to improve the design and management of systems, and then we'll see how we can do it. So there's two reasons. One is on the hardware side and one is on the software. So on the hardware side, for a long time, computer architects had a relatively easy ride in the sense that anytime we needed more performance from the hardware, we could rely on the device technology to give us more transistors, more performance, without increasing the power dissipation and cost of the device. And that is no longer the case. The NAR scaling has ended. Moore's law is also slowing down. And that has pushed a lot of architects to look for more specialized solutions. So whether these are through special purpose chips or reconfigurable accelerators. And this kind of acceleration is also finding its way increasingly into cloud infrastructures. And despite the performance and cost and power benefits that these accelerators might have, they also take what used to be an almost entirely homogeneous system and convert it into an increasingly heterogeneous infrastructure. So that increases the complexity of managing this hardware. And then on the software side, we have a similar story, which is that traditionally cloud applications were built as monoliths. And I'll talk a little bit more about what monoliths and microservices are over the next few slides. And then over the past few years, we've seen a transition from monolithic applications to loosely coupled, but still interdependent microservices and serverless compute. And what I'm showing on the slide are some dependency graphs from production services using microservices. And what you can see from these graphs is that, again, despite the benefits that these new programming models have, they do increase the amount of complexity because of the number of dependencies between them. So we have this trend of increased complexity on the hardware side and increased complexity on the software side. And that's exactly why it makes sense to abstract away as much of that complexity as we can from the end user and even from the data center operator and use ML to automatically design and manage the system. So these are some of the reasons why we might want to use ML. Let me also tell you why we can use ML today in a way that we couldn't necessarily 5 or 10 years ago. And the first reason is that at this point, we have been operating cloud systems for enough years to have collected massive amounts of tracing data from the monitoring infrastructures that are always in place in the systems. So there's a lot of knowledge that can be mined from this data that can help us optimize the way the system is designed and managed. The second reason is that there's been this explosion in machine learning research over the past few years, and that has yielded algorithms that are much more scalable and much more practical, which means that they can be applied at the scale of a cloud infrastructure where they couldn't necessarily 2 or 3 years ago. So this is an approach that can be applied across the system stack using ML to optimize systems. And a lot of the work that we do in my group is from the hardware level. So figuring out what is the right way to design the servers that populate data centers, what is the potential of acceleration that these new application models have, to cluster management. So what is the right way to manage resources for the systems? What are the right programming frameworks? And even what is the right way to write applications that run in these cloud infrastructures? So what I'll do today for the rest of the talk is use the microservices programming model as a use case, as an example of increased complexity in the data center, and as a motivation for why we may want to use machine learning to optimize their management. So I'll talk a little bit more about microservices over the next few slides, but as a quick takeaway, they have several advantages and several challenges. So in terms of advantages, they promote modularity and software specialization that makes it faster to develop complex applications and also continuously deploy them. Now, on the negative side, because they have dependencies between them, you can have cascading performance issues that propagate across the system. They are also much more sensitive to performance unpredictability. So they require microsecond level latencies as opposed to millisecond, which would be for a traditional cloud application. So given these advantages and challenges, what I'll talk about is a specific application of ML for the management of microservices, which is for performance debugging. So essentially identifying the root causes behind poor performance in a graph of microservices and applying automatic actions to avoid the performance degradation or quickly correct it. And I'll talk about two systems, Seer, which is a proactive debugging system that uses supervised learning techniques, and Sage, which is again, an ML-based performance debugging system that optimizes the scalability and practicality of ML. So it relies entirely on unsupervised learning so that you don't have to label manually tracing data. Okay, so I'm sure many of you are already familiar with what monoliths and microservices are, but just to make sure everybody's on the same page, what I have on the slide is an example of a monolithic application. So we still have the web server on the left and the databases on the right that are separate. But essentially the logic of the application, so all the functionality that implements, let's assume in this case, a social network. So the way to add posts, to see advertisements, add photos, get recommendations for other users, that is all a single application. And it's deployed as a single binary. And if at any point in time it needs more resources, you have to scale out across multiple machines the entire application. Now, as long as the application remains relatively small in scale and complexity, the monolithic design is fine. The problem is that when the application increases a lot in scale and in complexity, it makes it very difficult to continuously develop and deploy the application. It also makes it hard to adopt new software frameworks, so you are limited to the language that the whole application is written in. And like I mentioned before, it doesn't really help in terms of scalability because even if one part of the application needs more resources, your only solution is to scale out the entire application across multiple machines. So for these and for some additional reasons, a lot of cloud providers have moved to the microservices programming model, which essentially argues for very fine-grained modularity in application design. You have, instead of one large application, a graph of many smaller specialized applications that each target a small subset of the overall functionality and talk to each other over the network. There are several advantages to this. The primary one is modularity. So if you're in a large company, it makes it much easier to understand what the application is doing because you mostly have to understand the component that you're responsible for and the API to talk to the other components. So that makes it faster to develop and deploy the application. You can elastically scale the individual microservice that might need more resources instead of the entire application. And it enables some heterogeneity on the software side. So you can have different languages or programming frameworks depending on what language each microservice would benefit from. Now, that does not mean that microservices don't also have their challenges. So for one, we've replaced one large application with a graph of hundreds of smaller applications. Each of them has its own resource requirement, and they are connected over the network. So we need low and predictable latency in terms of the network communication. And even though they are loosely coupled, they're still dependent on each other. So we can have cascading performance issues that propagate across the system. So now, given the prevalence of this programming model, a few years back, we wanted to see what are the implications that it has across the system stack. So from hardware design all the way to applications application design, and programming frameworks. And of course, anytime you want to do a study like this, you need representative end-to-end applications that are built with a programming model that you're trying to study. And at the time, there weren't any available applications built with microservices. So there's been a lot of work in the academic community on building cloud benchmarks, but they primarily focused on monolithic applications or services with a couple of tiers. So over the past few years, we went into this effort of designing a representative benchmark suite that consists of microservices. We used a few design principles, so we relied on open source whenever possible, so that the components, the individual components, were in use in production systems. We made sure the applications are extensible, so if people are interested in adding new functionality, they can do that easily. They were configurable, and they capture diverse behaviors from different production systems that use microservices. So overall, we have 6 applications, end-to-end applications in the benchmark suite. Each of them consists of a few tens of unique microservices, and they correspond to different types of functionality. So from social networks to e-commerce sites, hotel reservation systems, and even some applications that run on Internet of Things style edge devices. And by the way, this is an open source benchmark suite. So if this is an area that you're working on or you're interested in, feel free to give it a try. We always welcome feedback and contributions. So I'm not going to go through each application, but I want to give you one example so that you have an idea of what their structure looks like. So this is the structure for the social network application. You can think of this as a very simplified version of Twitter. So it's a one-directional follow relationships social network with a broadcast style post distribution. So from the leftmost side, we have the client. They will send requests that will first hit the front-end servers. Then we have all the logic tiers that implement the functionality, and then we have the backend databases. And depending on what type of request a user might send, a different fraction of the dependency graph would be involved. So for example, if a user wants to log into their account, only a few microservices would have to be involved. If they want to add a new post and potentially add videos and photographs and links to that post, a larger fraction of the dependency graph would be involved. And the other services also have similar dependency graphs. Now, having these applications, we did this characterization study of what are their implications across the system stack. And there's a lot of implications at the hardware level, at the operating system and networking level. What I'll focus on here are the implications with respect to cluster management. So specifically, because microservices depend on each other and because systems are not perfect pipelines, you can have effects of back pressure, where essentially one bottlenecked microservice propagates its bottleneck across its dependent tiers towards the front end. So this is what the left graph here shows. This is an example from the social network application. On the x-axis, we have time, and on the y-axis, we have the individual microservices from the backend databases at the top all the way to the front-end web servers at the bottom. So they are ranked based on their position in the dependency graph. And the color of the figure shows the latency increased compared to nominal operation. So at some point at the beginning of time, one of the backend databases experienced a significant increase in its latency. And because of the dependencies between tiers, that increase in latency propagated all the way to the front end. So these kind of performance issues are very difficult to diagnose, and they can also take a long time to recover from, as the figure on the right is showing. So this is a comparison between the same application built as a monolith and built as microservices. And you see that from the moment a performance issue is identified, it takes much longer for the microservice application to recover compared to the same application built as a monolith. Okay, so why is that the case? Let's see an example of how performance debugging systems work in typical cloud providers today. On the right side, I have a couple of dependency graphs from 2 production systems that use microservices. And the way to read this is that the perimeter of each of these figures are the individual microservices, and then edges between points are the dependencies between microservices. So that's for Netflix and Amazon and one of our end-to-end applications. Now, if I have a typical performance debugging system that will only take action after it notices that there is a performance issue in the system, it takes a long time for it to recover. So on the left side, I'm showing the dependency graph for the social network from the front end to the logic tiers to the backend databases. And at the bottom, I'm showing the end-to-end performance in terms of tail latency. So if the dot is blue, that means that the quality of service or SLA is met. And if it's red, it means it's violated. So let's see how this works for a typical performance debugging system. So at some point, the application experiences a significant latency increase. which means the performance debugging system will take action and try and see which tiers, which microservices are running out of resources and give them more resources. Now, because utilization is not necessarily a good proxy for performance, you might have microservices that have high utilization but don't cause performance issues. And more importantly, the other way around, microservices that cause performance issues but also have low utilization. So because of that, it takes a long time for the performance debugging system to identify the root cause of the performance issue, and it takes a long time for performance to recover. So instead, what we try to do with this first system, with Seer, is see if we can leverage machine learning to apply proactive performance debugging action. So mine the large amount of traces that we already collect in the system, identify patterns in space and in time that signal an upcoming performance issue, and take proactive action to avoid it. So we rely on two levels of tracing for this. One is a distributed level tracing. The other one is per node hardware monitoring. And we also use a machine learning model. So for this specific case, we use a deep neural network. It's a hybrid model using a CNN and an LSTM, where the output is the probability that a given microservice will be the root cause of a performance issue, and the input signal is the number of outstanding requests ahead of each microservice. And other signals like per microservice latency are also possible. The reason why we're using a hybrid model is because we need to filter out noisy microservices that may not necessarily cause performance issues. So that is where the CNN helps. And then the LSTM is more geared towards near future prediction. And we've compared this to other simpler models that may only use a CNN or only an LSTM. Now, the way the system works is that the training will happen once unless the application or underlying hardware changes. And the way we train is by labeling, tracing logs with the root causes of QoS violations. The way we know the root causes is by injecting microbenchmarks that will cause quality of service violations. And then inference happens continuously while the system is running as traces streaming. And the validation we've done is on a dedicated heterogeneous cluster with a few of the applications I previously mentioned. So this graph shows a quick snippet of the validation study as we change the window over which we're trying to estimate the root cause detection. So if we try to predict very near into the future, so just a few tens of milliseconds, then the accuracy is very good, but we don't have enough time to react. And then on the inverse, if we try to predict very far into the future, both the false negatives and false positives increase. And the reason for that is because a lot of performance issues in the cloud are caused by burst events. So if you try to look too far into the future, you won't be able to capture these events. Now, once you identify that there is a microservice that's creating performance issues, what can you do about it? You can use one of multiple resource isolation and partitioning techniques to allocate more resources to the problematic resource of that microservice. So depending on what resource is problematic, you can use things like scaling up or scaling out, power management, cache partitioning, memory capacity or bandwidth partitioning, network bandwidth partitioning, and so on. There's still a few types of performance issues that are not resource related, so they might be design, correctness related. And in those cases, Seer will eliminate all the resource related performance issues. And if it's a bug that somebody has to address, then a person will need to be involved and look through the code. Okay, so let me quickly show you a quick demo of how the system works compared to a default performance debugging system. So on the left is Seer, on the right is the default system. Again, we have the social network application. Each of the circles is a microservice. And then in the bottom, we have performance. If it's blue, performance is good. If it's red, performance is good. Okay, so initially, requests are starting to flow through the system. And if we wait a little bit, we'll see that the system on the right starts to experience performance degradation. So its tail latency will increase pretty rapidly. Now, because it only relies on resource utilization to identify the root cause of the performance issue, it will take a long time for performance to recover. And not only that, but also the performance issue will propagate across the dependency graph from the backend services towards the front-end services. Now, by comparison, and we'll see the latency.
30 seconds.
Okay.
You have.
Let me skip the rest of this and go to the end. So every time I give a talk like this, one question that I always get is, how do we ensure that the machine learning techniques we apply are explainable so we can get some insight out of the output of the model? And an example that I'm showing here is the number of performance events that we noticed in the social network application over a 2-month period given the feedback that we got from the Seer system. So to conclude, both the hardware and software side of cloud systems is becoming
any window